All right, still talking about ionic compounds a little bit, and we want to show an important property of ions. Ions conduct electricity. Now, this concept of conducting electricity is sometimes portrayed in images like this and misconstrued into thinking that ions are creating electricity. So I'm going to take a little bit of time to explain what conducting electricity means. So here's a light bulb, let's say, and here's the part that you screw in. There's a little bump at the bottom there. Here's the bulb itself, and here is a wire inside. The wire inside is connected to these threads on the outside and connected to this, the bump there on the bottom, all right? And I need to have a wire connect to the threads and connect to the bump and then connect to some sort of power source. Usually it's, the power source that's like this on the side of your wall, right? You can plug it into that sort of thing and you can get power out, right? The power source that we're going to be interested in plugging into is going to be, we're going to represent by some 9-volt battery here or something like that, okay? So I need to connect these to this battery, and when I connect them, then I'll get some light from the electricity that's running through that wire and creating resistance and creating light, okay? But if I'm not connected, I won't get any light. If I take a wire connection here and bring it very close to this wire, still no connection, still no light, but then I place these two connections into something like water, right? If I place water in there, water is still not conductive enough, or is not conductive. It's a molecular compound, and so it still won't produce any light. However, if I put something like salt in that water, and that's what we're seeing up here, pure water will not produce conductivity to allow light to a light bulb to turn on. But if I put salt into the water, then it will make the water conductive. Okay. If I have solid sodium chloride, no conductivity. But if I heat that sodium chloride until it melts, and that's just a physical change, then I do have conductivity as well. So I will get conductivity if I put in here not something molecular. Water is a molecular compound, but if I add in there something that is ionic. Okay. Now what happens when you put sodium chloride or some other soluble salt into water? The term salt is any ionic compound, and we'll remind you that of that as we go. But if I put an ionic compound into water that's soluble, the ions separate from each other. So I have sodium ions and chloride ions separating from each other, and I get conductivity in the water, and the power source can help to light up. Okay? All right. So once again, molecular compounds do not create this. If I have water in there, which is a molecular compound, I do not get any electricity generated. Or not electricity generated, no conductivity, right? No flow. All right. So how can we combine ions and identify what the resulting compound is going to form? Here's an important video that I just alluded to. Here we're taking a crystal of sodium chloride. Okay, this is a crystal of sodium chloride, and the sodium ions are the small ones, and the chloride ions are the green ones, the larger ones. Chloride ions are larger because they've gained an electron. Sodium ions have shrunk because they've given up an electron. We talked about that previously. And this is how sodium chloride resides at room temperature. It's what we call a three-dimensional lattice. Can you say that, Fred? Three-dimensional lattice? Yes, three-dimensional lattice. It's important to recognize that three-dimensional lattices are how ionic compounds reside. Okay? If you look at something like this, one of these, like here, let's look at this chloride ion right here. How many neighbors does it have? How many direct contact neighbors? 1, 2, 3, 4. I can't tell. What are we looking at there? Well, we have one above, one below, one to the right, one to the left, and there's one inside here, And if this was inside it, there would be one in front as well. So there's 6 neighbors. Can you see that?
Yeah, I guess I can see that. What about the corner ones?
These diagonal ones aren't in contact with it, okay? But this here, let's look at this sodium ion right here. It has 1, 2, 3, 4, one down below that we can't see, and it would have one up above if this crystal were to continue, if this weren't the edge. So all of the ions here, whether they're sodium or chloride, positive or negative, cations or anions, have 6 neighbors, direct neighbors, contacting neighbors, okay? And that creates a stable structure. This 3-dimensional lattice is how ionic compounds reside, okay? And we'll talk about it later, but there's a lot of energy that is released as these ions come together. Now, if you place this in water, water dissolves this 3-dimensional lattice. And what's happening is the water molecules are surrounding these ions and providing the stabilization that the ions were receiving in this crystal lattice. The water molecules are providing that now. And so that it allows those ions to separate from each other, and the whole 3-dimensional structure dissolves, but we also call it dissociates. Dissociates. That's a special word to say that it's not just dissolving in water, but that the ions are actually separating and being surrounded by water molecules. Okay? So that's how ions, what ions do. Ionic compounds that dissolve in water, that's how they dissolve in water. And we'll have a lot more conversations about that specific subject because it's critical to understand so that we can know how ionic compounds behave in aqueous solutions where they perform most of their chemistry. So looking at these ions, this is the aluminum ion, and what do you think this one's called? What's that one called, Fred?
The oxygen ion?
Okay, that was close. Oxygen ion is close, but it's not oxygen ion. Just like we didn't call this sodium chlorine. What's the name of this compound?
The sodium chloride?
That's right, sodium chloride. And notice that you said "ide" at the end, sodium chloride, and that's because this is the sodium ion and that's the chloride ion, right? Cl minus chloride ion, okay? So when we create an ionic compound from, let me bring in our periodic table here, from a metal and a nonmetal, the anion, which is the nonmetal, takes on the "ide" suffix, okay? So sodium chloride. So this isn't the oxygen ion, but the what?
The oxide ion?
That's right, oxide ion. So the combination of these compounds is going to be, these ions is going to be aluminum oxide, but we have to recognize that the way that they come together depends on the charges that they have. So the aluminum ion has a +3 charge, the oxide ion has a 2- charge, right? And so we can see that for those to come together, we're going to have, a 1-to-1 ratio doesn't work because there's no way that aluminum lost 3 electrons and one oxygen atom only took 2 electrons, right? It has to be equal. The amount of electrons that this lost has to be taken by the oxygen. And it doesn't have to be just a single oxygen. It can be multiple oxygens. So if aluminum is going to lose 3 electrons and form a +3 charge, I'll need more than one oxygen atom to take those 2 electrons. And to do that, that doesn't work. I have 4 electrons that are being taken now. So I need more aluminum, losing electrons, and now I need more oxygen. And I can do that until I identify that the amount of electrons lost here now matches the amount of electrons gained. You see that, Fred?
Yeah, I see that.
All right. There's a little bit of an easy way to look at this. It's called, a little crisscross rule here, where we bring that number down and put it in front of, or as a subscript to the cation, and the result, and same thing we've done with the anion, and the result is the chemical formula that will result based on those charges. Okay? So Al2O3 is the resulting compound when you combine aluminum with oxygen because of the kinds of ions that they'll want to form. Now, if we just had the periodic table, we could again look at aluminum, see that it's element 13, and that it needs to go to have 10 electrons to attain a noble gas electron configuration. What does it do if it has 13 electrons and it needs to get only 10? Fred, what does it need to do?
Lose 3 electrons?
That's right, and that's where we get that positive free charge, right?
Yeah.
Okay, so oxygen, let's look at it. Its location on the periodic table. What does it need to do to attain a noble gas electron configuration?
Gain 2 electrons.
That's right, it needs to gain 2 electrons. All right, and so that was a review on how we know how to predict what kind of ions are going to form, and then we can see how those ions are going to come together so that the amount of electrons lost is equal to the amount of electrons gained. Good. Let's do that with magnesium oxide. Same thing. This time, however, the resulting compound would be something like this, Mg2O2, if we just use the crisscross rule directly. But ionic compounds are not like molecular compounds. Ionic compounds are always provided in their empirical formula. So this is going to be MgO only. Ionic compounds reside as, what do you call it? Three-dimensional what?
Lattices.
That's right, three-dimensional lattices. They always reside as three-dimensional lattices, and so it never makes sense to give anything but their empirical formula to represent that compound. Magnesium oxide is an ionic compound. It doesn't reside as just one magnesium and one oxygen. Chemical formulas for ionic compounds are only ratios of the resulting of the atoms in the compound, right? Okay, so that's the chemical formula for magnesium oxide. We can do the same thing with our polyatomic ions. We take our polyatomic ions, we look at their charges, and we recognize that we're going to need more of which one? Which one are we going to need more of, Fred?
What are the names of those ions?
That's a good question. Let's bring it up here. Let's bring up our polyatomic ion chart. All right. What do we got there?
Well, that looks like it says the ammonium ion.
That's right. The ammonium ion, NH4+, right here.
And the phosphate.
All right. Phosphate ion. Where did you find that one?
Well, that was up top.
Okay, there it is, the phosphate ion. All right. So we have the ammonium ion and the phosphate ion. And those ions, need to come together in a ratio to make sure that the number of electrons lost equals the number of electrons gained. Okay? And what do you think?
I'm going to need 3 ammonium ions.
All right, so we're going to have 3 of these NH4 pluses, right? For every, how many phosphates?
Just 1 phosphate.
All right, PO4 3 minus, okay? And the resulting compound is going to be NH4. Now we put parentheses around our polyatomic ions to make sure that we recognize that we're trying to use this subscript to show that there's 3 of those polyatomic ions. But this is the chemical formula for that compound. What about its name? What do you think?
That was the ammonium ion and the phosphate ion?
That's right.
Is it just ammonium phosphate?
It is. For polyatomic ions, we just say the name of the polyatomic ion in the compound. Ammonium phosphate. Good stuff. Okay, good place to stop. Empirical formula and molecular formula. So we've used chemical formulas a little bit now, quite a bit, to explain chemicals. And we've talked about molecular and ionic compounds. And the molecular formula for a compound like glucose, we've talked about that a little bit as well, C6H12O6. Let me throw in a couple others that we've talked about. Water, chemical formula for water. This is a chemical formula for hydrogen peroxide. You may remember this compound. This is another chemical that we've talked a lot about, carbon dioxide, all right? So these are these two are our standard molecular compounds, and H2O2 is a new molecular formula here that I'd like you to be aware of. Okay, and we call these molecular formulas because this is how the molecule exists as it does whatever business it's going to do. So this is 2 oxygens and a hydrogen. This is carbon dioxide, like that. Okay. So these are called molecular formulas because that is what the molecule looks like when it's doing its interacting with other compounds and so forth. We have something that's called the empirical formula, which is the simplest ratio of the molecular formula. Molecular formula for glucose has an empirical formula of just CH2O. Does that make sense, Fred?
Yeah, I get that.
Now, I'd like you to also recognize that between the empirical formula, so here's the empirical formula of glucose, and here's the molecular formula of glucose, C6H12O6. Between these two, there is a multiplier, right? There's a multiplier. And if we call that multiplier N, for example, you multiply times N to get from here to there. What's the N value in this case here, Fred?
You mean like multiplying by 6?
That's right, multiplying by 6. So N equals 6 here. So if you multiply by 6, this times 6, that gives us, the empirical formula times 6 gives us our molecular formula. Okay, good stuff.